All right, good morning. My name is Liv Pollock, and today I'll be presenting my research developing and assessing Fucose-Based water-soluble bioplastics. For decades, marine organisms have suffered at the hands of plastic waste. And in fact, it's been found that annually over 6,000 marine organisms die due to unintentional plastic entanglement or ingestion. The plastic pollution of the world's oceans is a global issue. And on this map, the darker shaded regions indicate higher incidences of plastic waste. In fact, it's been found that annually over 8 million tons of plastic waste are leaked into oceans, and this number has not yet to see a decline even in recent years. As a result, more biodegradable alternatives are being studied in order to combat this. A study done by Hayatin, Jana, Ahmad, and others that was published in 2020 looked to develop a bioplastic film composed of rice husk cellulose. The product was designed with the cultivation of food resources in mind, and they ultimately created a product in which 57% of it broke down within 6 months. Another study by Rosenblum and Zhao that was also published in 2020 developed biopolymers composed of soy protein isolates. Their products were designed to be intended to be used for future food packaging and were known to express high elasticity, antioxidant, and preservative properties. However, another study by Napper and Thompson back in 2019 found that most commercially available biofilms do not even break down after multiple years of exposure to natural environments. This image is of an unearthed plastic bag approximately 3 years after it was initially submerged in a natural environment. However, this same bag is listed as being able to break down within only 3 months. As a result, more water-soluble bioplastics are being developed and studied in order to combat this. A study that I conducted that is currently in the process of being published combined the use of polyvinyl alcohol and carboxymethyl cellulose as a bioplastic base. I ended up creating a product in which 61.9% of it dissolved after 48 hours of testing, along with the fact that it did not significantly alter its environment's pH level. However, throughout my research, I also concluded that while PVA and CMC are water soluble and non-toxic, they're still synthetic materials. So if they were ever to be released into the environment on a massive scale, there's still the potential that they could harm marine organisms. Therefore, the purpose of this research is that given there is currently no published literature regarding the development of water-soluble biofilms that are entirely composed of natural materials, I aim to remedy that. And throughout my research, I encountered two bases that I wanted to incorporate into my research. The first one is fucose. Fucose is a monosaccharide found within the cell walls of most microalgae. So since it is currently found within marine ecosystems, its reintroduction back into them is not considered invasive. In fact, its cultivation is arguably beneficial given that the algae it's been found in has been known to grow over both sea sponges and coral. This in turn blocks sunlight and then ultimately kills the plants. In fact, it's actually safe to be consumed once in a powdered form as well. Along with that, I also aim to combine it with citric acid. Citric acid is found within most citrus plants and has been studied as being a natural plasticizer and binding agent. Citric acid has also been known to reinforce biofilms and ultimately increase product malleability, which in turn expands their potential uses. Throughout this research, I had multiple objectives. I aimed to engineer my new bioplastics while recreating my previously studied samples, to assess solubility in both freshwater and 3.5% saline media, and to measure biodegradation in a controlled environment. Along with these objectives, I also had multiple hypotheses. I believe that there would be a difference in the dissolution between the two types of sample, that the PVA plastics would alter their environment's pH levels more than the fucose ones, and that there would be differences in the rates of biodegradation between the two types of sample as well. My methodology ended up being divided into three distinct subsections. During phase one, I engineered my Fucose-based plastics. In phase two, I recreated my previously studied PVA ones, and then I measured solubility and biodegradation. So during phase one, my experimental variable was the concentration of Fucose within each sample, in which I ended up developing four distinct products. Those that were 25%, 50%, 75%, and 90% Fucose by mass. My 25% sample served as my control group, given that it contained equal amounts of each of the following materials. And that would be agar powder, dried algae shavings, citric acid, and water. During phase two, these were taken from my previously established methodology, in which I once again developed four distinct bioplastics with varying levels of PVA by mass. They were designed to be directly compared to their Fucose counterparts and thus not only underwent the same testing methods, but also intended to serve as all expected values during statistical analysis. In terms of measuring solubility, this is performed in both freshwater and 3.5% saline media. And the purpose in doing both of these was to best mimic Earth's natural conditions without possibly exposing marine organisms to biofilms that had never been studied before. Since solubility was measured after both 24 and 48 hours of testing, along with recording each environment's pH level at these intervals, I concluded that each product's percent dissolved would be equivalent to its environment's percent change in concentration, and performed paired t-tests with alpha levels of 0.05 to compare everything. Along with measuring solubility, I also compared biodegradation. So this was performed in a damp soil-rich controlled natural environment in which the masses of each sample were recorded weekly for 6 weeks. I determined that each product's percent biodegraded would be equivalent to its percent change in mass, and intended to perform chi-square tests for homogeneity with alpha levels of 0.05 to compare them as well. So this is a graphical representation of the dissolution of the PVA samples in the freshwater environment. And as can be seen, the 90% PVA sample dissolved the most with a total of 72.55% dissolution after 48 hours. This graph is showing a similar trend except for the dissolution of the PVA samples in the saltwater environment. And once again, the 90% PVA sample dissolved the most with a total of 29% dissolution. And these two values are going to serve as baselines to compare the Fucose dissolutions to. So this is a graphical representation of the dissolution of the Fucose samples in the freshwater environment. And now the 90% Fucose sample did dissolve the most, but only with a total of 63.24% dissolution. So given that this was less than the dissolution of the PVA samples, I concluded that under the same freshwater conditions, the PVA samples were more effective. However, once the salinity of the environment increased, the 90% Fucose samples still dissolved the most, but with a total of 34.8% dissolution. And given that this is higher than the 29% dissolution of the PVA sample, I concluded that under the same saline conditions, the Fucose samples were more effective. These two graphs are comparing changes in pH level for all the freshwater samples for both the PVA and Fucose products. All of the PVA samples, regardless of their concentration, maintained an approximately neutral pH around 7 throughout all experimentation. However, all of the Fucose samples, regardless of their concentration, the pH of the environment went from being approximately neutral around 7 to dropping to highly acidic around a 3, all within the first 24 hours of testing. And this data is supported by p-values of 0.07 and 0.0001 respectively. Thus, I concluded that there was no significant change in the pH level attributed to the PVA samples in the freshwater environment. However, there was for the Fucose samples. These graphs are comparing similar trends except for the change in pH level of the saltwater environments. And once again, for both the PVA and Fucose samples, they are each expressing similar trends as seen in their freshwater counterparts. And this data is supported by p-values of 0.25 and 0.00008 respectively. So once again, there was no significant change in the pH level of the 3.5% saline environment for the PVA samples. However, there was for the Fucose samples. Now, these images were all taken approximately 1 week after exposing all of the samples to the natural environment. The two on the right were attributed to PVA samples, and those on the left were for Fucose samples. Specifically, within each of these red boxes is where all of the samples were initially submerged. And as can be seen, there are no fragments of microplastics present within any of them. Thus, I concluded that after only 1 week of exposure, all of the samples, regardless of their concentration of either Fucose or PVA, had completely biodegraded. And this is huge, according to that Napper and Thompson study back in 2019 that found that most commercially available biofilms do not even break down after multiple years. So to iterate what was mentioned earlier, my first hypothesis in which I claimed there would be a difference in the dissolution between the two types of sample was ultimately refuted. This is because the only significant difference occurred after all 48 hours of testing only in the 3.5% saline media. So since none of the other differences were statistically significant, I elected to refute this hypothesis. My second, in which I claimed that the PVA plastics would alter their environment's pH levels more than the Fucose ones, was not only refuted, but the opposite was found to be true, given that all of the p-values attributed to the change in pH level for the Fucose samples were less than alpha, thus rendering them statistically significant. And then my final hypothesis, in which I claimed there would be a difference in the biodegradation of the two types of sample, was ultimately refuted given that it was also inconclusive. This is because biodegradation was intended to be assessed weekly, however, all of the samples had completely biodegraded after only the first week of exposure. The study definitely had its fair share of limitations. For one, I was not able to directly regulate the temperature of each of the aqueous environments. Now, that being said, the room that all dissolution experiments were performed in never fluctuated by more than 1 degree Celsius, and this change is in fact considered negligible when measuring rates of dissolution. Along with that, I also found that my previously studied plastics work better than my newly developed ones. And what I mean by that is that the PVA samples dissolved more and altered their environment's pH levels less than the Fucose samples. Nonetheless, the limitations limitations of this study should not overshadow its novelty. For one, there is currently no mainstream water-soluble biofilm that is commercially available. And as for existing biofilms, not only are they not able to dissolve in water, but very few of them are entirely naturally derived, with PVA being a common base among many of them. And then ultimately, nothing similar to this research has yet to be published. So in conclusion, despite a lack of statistical significance, great headway has been made. For one, 63.24% of the 90% Fucose sample had dissolved within 2 days. So not only was this, while this was still less than the 90% PVA sample, not only was it still the majority of the sample that ended up dissolving, it was able to dissolve when current bioplastics cannot. Along with that, all of my studied samples had completely biodegraded after only 1 week of exposure to the natural environment. And this is crucial according to that Napper and Thompson study from 2019. So in the future, I would like to begin by finding a way to neutralize the Fucose-based polymer. And this is because all of the Fucose samples, after only a very short period of time of being exposed to the aqueous environments, drastically altered their environment's pH level. I would like to go about this by combining the citric acid with a more alkaline material, such as maybe xanthan gum, in order to continue creating water-soluble biofilms, but ones that are more neutral. I would then like to transfer this research to a more traditional experimental location. Given that I performed all of this experimentation working from my home and was thus a little bit limited in what I was able to study, working in a traditional laboratory would make it easier to control extraneous factors, such as temperature, that have been known to alter rates of dissolution. Along with that, I would be able to assess other properties that need to be looked at when developing biofilms, and this includes but is not limited to tensile strength and strain at break. And then ultimately, the final goal of this research is to replace conventional six-pack soda can rings in industrial settings. The study is significant given that this is an image taken off the coast of the Florida Keys coral reef back in 1980, and as you can see, it is full of life, and this is prior to the boom of most plastic pollution. This image is of the same coral reef taken back in 2020, and as you can see, it is completely devoid of life. Thus, this project has the potential to begin to restore ocean habitats, remove harmful algae, and ultimately decrease overall global pollution of the world's oceans. I would like to acknowledge my mentor, Mr. Christian Abraham of Corning Incorporated, my science research director, my science research teacher, and my friends and family for supporting me throughout the process of actually getting a patent for this project. These are my references, and that concludes my presentation. Thank you.